So one important topic in chapter 3 is to be able to distinguish 4 different types of matter. Okay, they're in 2 broad categories. You got pure substance versus a mixture. Okay, and within that pure substance category, you have element and a compound. And then within the mixture category, you have difference between a homogeneous mixture and a heterogeneous mixture. Okay, so first off, let's just sort of briefly talk about a pure substance. And when I talk about a pure substance, when I reference a pure substance, there's going to be some reference to the periodic table. Right? And there's 2 examples in this list here that would be in the category of a pure substance. One is an element, one is a compound. Okay, let's just look at the periodic table real quick. I'm going to be very specific when I talk about a pure substance. I'm going to pull, some kind of notation from the periodic table. Okay, so if it's a single element, that's going to be an element. Okay, and then if it's more than one element, and I'll just do a common one here, like sodium chloride, then that's going to be a compound. Now, the reason why I circled mercury here, well, is because you see that language in A, mercury in a thermometer. So knowing the symbol and the names for the elements in the periodic table can be very useful. There's a short list of elements to know, and that is available on Moodle. So if you see a reference to a single element on the periodic table, then that's an element, right? So it's number 1 of the different classifications for matter. Now, the other pure substance down here is actually D. Now, on a test or any question that I generate, I always reference, I don't just give the common name, okay, because that's a little unclear, especially when you're first getting into chemistry. Okay, so, for example, if I talk about sugar, I will give you the specific formula. You don't have to know details of the formula. You just need to recognize the fact that the C, the H, the O, carbon, hydrogen, oxygen, well, again, that's notation coming from the periodic table, right? Carbon, oxygen, hydrogen. So again, a single element on the periodic table being referenced, that's an element. 2 or more, that's a compound. So sugar, with this particular formula, which I would give you on a test, that would be a compound. Now, the other 2 examples here are going to be mixtures. And there's 2 different classifications here. There's a homogeneous mixture and the heterogeneous mixture. And it really boils down to, do you have a uniform appearance? Okay, so a heterogeneous mixture has a non-uniform appearance. Right? There's at least 2 things that are distinct. The chicken broth and the noodle. The broth and the chicken. If you can pick out 2 specific features that are physically different from one another, then you're going to be dealing with a heterogeneous mixture. Whereas a homogeneous mixture, well, it's made up of 2 or more compounds or elements, and the main point here is it has a uniform appearance. And of course, air is an example here. Now, how do I know that these 2 are not elements or compounds? Well, there's no specific reference to an element on the periodic table. There's no element called chicken. There's no element called noodle. Okay? There's no element called air. Again, especially for, fundamentals of chemistry type of course, I'm going to give you a very specific reference if I'm dealing with an element or a compound. If you don't see notation referencing the periodic table, then it's going to be a mixture. You just need to determine, is it uniform or non-uniform appearance to distinguish between homogeneous and heterogeneous. A second important topic in chapter 3 is this idea of, are you dealing with a physical property or physical change versus a chemical property or change? First off, let's look at the physical. What are you looking for to distinguish that, yes, this is a physical process or a physical change or a physical property, okay? This is talked about in more detail in the lecture, but basically it's something that is happening to the substance or a description of the substance that doesn't actually change the substance. For example, something dealing with phase, something dealing with color, odor, okay? Anything dealing with appearance. A physical property like a melting point or boiling point. Density, that's a physical property. You know, if I talk about water boils at 100 degrees Celsius, that's just a statement of physical property, you know. Water would, if I was boiling water, right, just watching a phase change going from a liquid to gas, it started out as water, liquid water, and then it winds up as vapor, gaseous water, still water. That is a physical property, a physical process, okay? So of the ones that are listed here, well, one thing, we have a couple that, you know, just staring at me, color, appearance. You know, I can describe the bronze color of copper, and copper doesn't change, you know, when I talk about that. It is a physical property of that substance. The shiny appearance of silver or any metal, that's another physical property. Notice in D is actually, you know, sublime. We saw it in a lab number 2 and 3, actually. So that ammonium chloride in lab 2 would sublimes from the mixture when you heat it in the first step. And the first reaction of experiment 3, the iodine sublimes. And we talked about that being a change from a solid to a vapor or to a gas. Right, iodine, starting out as a solid, heat it in a hot water bath, you get that purple gas. Starts out at iodine, it's still iodine. So any kind of physical change is a physical property. Chemical, however, the substance changes. And we'll see this aspect in a future lab. But when you talk about chemical change, there's something that, there's always some clue that accompanies that chemical change. There's a heat change, gas evolves, light produced, color change. Like, for example, if I describe the bronze color of copper changing to more of a green patina or something, I think of the Statue of Liberty. That's a result of a chemical change. Statue of Liberty started out as a bronze color because it's primarily copper. And over time, that copper oxidizes with the air and water in the atmosphere, and it turns that green color. So that was that, like a permanent color change. That's an example of evidence of a chemical property or chemical change. And if I look at the list, right, the only one left, A, explosiveness of hydrogen gas. An explosion is a chemical change. Chapter 3 includes a discussion about energy, different forms of energy in the world. So briefly, there's a bunch of different types of energy. Kinetic, potential, heat, work, all these are energy. Energy associated with food, nuclear processes. But no matter what type of energy you're talking about, they all share a common set of units. And the two main ones, calorie and joules. There's some conversion factors. These would be given to you, okay, for the test. And you're really just using your dimensional analysis knowledge of how to do these different types of calculations. Well, let's just sort of work through this one here. So a match burns, kicks off a certain amount of heat. It's first measured in calories, okay? And we want to know how many kilojoules are in there. This is a conversion factor, this is a dimensional analysis problem, very much like what we saw in chapter 2. It's just now we have different units. We have units dealing with heat. And just like before, you got to find your path. And I'm going to go ahead and ink this in. There's not a single conversion factor that allows you to go from calorie to kilojoules. One thing to note is that calories and joules, they're kind of on the same level of degree, okay? Same sort of amount of heat. Whereas kilo of anything is a larger amount. So classic kind of setup for dimensional analysis. We go from a common unit to the metric unit, requires a conversion factor. And then we go from something that's a small measurement, in this case heat, to something that's really referencing a larger amount of heat, kilojoules, that requires a second conversion factor. The first conversion factor here is just simply going to be that there. 1 kilojoule equals 4.184, 1 calorie equals 4.184 joules. And then between these two, well, we have to rely on our metric system. And so let me just sort of map out the conversion factor here. On chapter 2, we talked about doing something like this. Specifically, it was on the test review where I talked about this in more detail. But if you want to generate a conversion factor between kilojoules and joules, well, what does 1 kilojoule represent? Well, 1 kilojoule, what you can say here, keep the 1 and the joule, and then in place of the kilo, just use the prefix that we learned. This is our conversion factor now for this last step. Let's put it together. Start with what's given. I know there's 2 steps. I'm going to have 2 of these, what I was calling mathematical templates for my calculation. First conversion factor is right here. I'm starting with calories, so it's this portion of the conversion factor that's going to go on the bottom. And then now, if we sort of pause for a second and think about what we're doing, calories would cancel out. We're left with joules. And so now, joules, which portion is going to go on the bottom? This portion is going to go on the bottom because I want joules to cancel out. And notice what happens. Joules cancel out. And now the only unit left is kilojoules, which is, of course, what we want. Mathematically, right, anything that is on top of the expression is going to be multiplied by. Anything on the bottom of the expression is going to be divided by. If you plug and chuck this, you get 2.142208. And that's kilojoules. Now, just like we saw in chapter 2, just like you do with any calculation in this class or any chemistry class, any science class, you want to round off properly. Your calculator doesn't know, at least my calculator doesn't know how to handle sig figs, so I have to go in and do it manually. The data that's given, I have 3 sig figs on that one, and so I want to keep the first 3 sig figs that I see. This next digit down is less than 5. And so basically I'm just going to drop that portion of the expression. The correct answer would be 2.14 kilojoules. The last set of calculations in chapter 3 is dealing with the heat equation. So heat equals mass times specific heat, and then the change in temperature. The C there's actually 2 variations. The specific heat capacity versus a specific heat. It's the same thing, okay? Sometimes you do rearrange this, solving for mass or delta T or C. That's possible. But this by far is the most common form that you're going to see in this class. And this is the form you're going to use for this particular problem. Now, word problems, and I'm going to do the top one there, can always be challenging, especially if this is the first time you've seen these kind of things or if it's been a while. Sometimes there's language like this first sentence, it really doesn't matter about that. What you're looking for are the numbers. The numbers are relevant. That's typically true. Okay, certainly it's true here. And then somewhere in the problem, there's going to be a question. What is? How much? That tells you what you're trying to determine. How much heat? Heat is represented by Q. Well, if I want to calculate the amount of heat, Q, then I need to track down mass, the specific heat, and the delta T of this in this problem. Okay, so the mass is given to me directly. That's good. So there's the mass. And then for the temperature, what you see here is the copper penny is warming up. Okay, so it's going from negative 5 degrees Celsius up to 37.0 degrees Celsius. And let's just take the temperature separately here. Let's talk about that delta T. So that triangle there, Think of it as like a capital D in the Greek alphabet, delta. And when you see delta in front of any kind of unit, what it's really getting at is change of something. Change of pressure, change of volume, in this case, change of temperature. And that change is always expressed as final minus initial. Okay? Always stick with that. That allows you to work out the proper sign in your calculation. So in this, when I read the problem, it tells me that the -5 is the initial temperature. This penny is found in the snow. And then you warm it up by holding it. The final temperature is 37. Okay, so we're just going to plug and chug. 37 degrees is the final temperature minus 5.0 degrees Celsius. Subtracting a negative number is essentially addition. Okay, and you can try that on your calculator. What that tells me is that the total change in temperature now here, 42.0 degrees Celsius. I am applying my sig fig rules here. Okay, it's simple enough to do. Whenever you're doing subtraction or addition, it's not the total number of sig figs that matters. It's actually the decimal place. And since both of these are coming in a decimal place of 1, then the answer from this portion is going to be at a decimal place of 1. Okay, so now I have delta T here. I have mass, right? That's just given in the problem. And then I can look up the heat capacity of copper. And I would give you that on a test. So I'm going to give you that here. So I'm ready to plug and chug. Heat capacity of copper, according to that table, is 0.385. Notice the units on this, joules per gram per degree Celsius. I'm going to come back to it in just a second. And then we just determine what the delta T is. Okay, so one thing to keep in mind when you're doing any type of calculation is that the units agree with each other when you're calculating. Like for example, if this had been in kilograms, then you would want to change this to grams before plugging it into this expression. If this had been in Fahrenheit, then you would want to change it to Celsius before plugging it into the expression. All these equations would be given to you on the test. Okay, all these constants would be given to you on the test as well. And you see, if I multiply all three of these together, grams, degrees Celsius cancel out, and we're just left with joules, which, right, that is our unit for heat. Joules or calories, right? Those are our units for any type of energy. If I plug it on the calculator, I get 50.127 joules. And just like any type of calculation here, right, I want to factor in my sig figs. There are 3 sig figs there. This is usually just, if you're looking up data on a table, typically I just say ignore that. So I'm just going to focus on the data that's given in the problem. Right? And what I'm looking at, 3, and even if I did factor this in, there are only 3 sig figs there. Anyway, 3 and 3, you're going to round this off to 3 significant figures. Since the next digit down, again, that was a 2. It looks messy, I know. But, right, 4 or less, you just drop this portion of the expression. So the correct answer here is that penny absorbed 50.1 joules of energy when it did that particular temperature transition. That's it. Thanks.